Hi everyone. So we're in our code now. This is the code for assignment 9 that I have given you. And again, for assignment 9, what we're going to do is we're going to implement a map ADT. And unlike assignment 7, where you did a hash map, now we're going to use a tree map. So this binary search tree is going to be our underlying data structure. Okay. Now, the components of the binary search tree are tree nodes, right? Those are the things that are going to hold our data values and have the left and the right children concepts. Kind of like linked list nodes, but on steroids. There's more to them. So we are making a map, right? And a map associates keys and values, just like a Python dictionary, right? So we want to be able to call things like tree, sub 850123456 gets Mike, right? This is kind of the dictionary style, the map style. So the way we will accomplish that is every node in our binary search tree is going to hold the key, and this is the thing that we're really going to care about the most in our algorithms, and the value that's associated with that key. So we've actually got 2 data points in each node, plus a variable that holds a reference to the left child, if there is one, and a variable that holds the reference to the right child, if there is one. Okay, so this is what we're going to put in our tree. All right, so here's our tree map. Now, just like the linked list, if you remember, the linked list only knew about one node, and that node was the head in the linked list. In our tree map, the tree map is only going to know about one node, and that's the root. Okay, so we are going to initialize our tree map to hold the root, and we initialize it to none. This means that the tree is empty. Okay, so let's go write our code that can insert data into this tree. All right, so here's insert. So by the way, you see all these raise not implemented error. As you go and complete your assignment, you're going to delete these lines. These are just here to support testing, right? So if you run the code just like with your other assignments, it'll run tests for you. So whenever you're ready to have one of these functions or methods be tested, go ahead and get rid of this line, right? It shouldn't be in your finished code. All right, so let's write the insert code. To do that, we're going to take our algorithm that we wrote and modify it just slightly. So insert method is going to insert data into the tree map, and we're going to do it recursively. The other thing that we have to worry about, now we're going to change it up just a little bit because we're dealing with a map, okay, or a dictionary. When the key to insert already exists in the tree map, replace the tree node's value with the new value, right? So this is to handle the case where, like, you previously called tree map non gets 1, 2, 3, and then later you want to reassign it, right? Non gets 999, right? So we got to handle this case as well, where we are replacing the value associated with the key. Okay, so let's do an insert. All right, so let's go back to your algorithm that you have on your binary search worksheet, okay, on the first page. All right, so let's just translate that into Python. If the item to insert is less than current.data, so you should assume, and this is what we are going to do, whenever insert is initially called, it will be called on the root node. So why don't I even put that in here? Insert will initially be called with cur equal to the root node. Okay. Where are we going to do that call? We're going to do it in set item down here in a minute. Okay, but let's not worry about that just yet. When we start, cur will be the root. You don't need to know that because this algorithm is recursive, though. Okay, the algorithm doesn't need to know if it's dealing with the root. It just needs to know what the current node is, whether it's the root or something else. All right, so let's translate that algorithm into Python. If the item we are inserting, the item that we care about is the key. Okay, we're inserting key value pairs. our binary search tree, we're going to organize it according to the keys of the dictionary, the keys of the map. Okay, so if the key that we are inserting is less than the current node's key value, okay, what do we need to do? That's like saying, all right, insert at value with key 1 and the current tree roots node, or the current node's value is 5. Where do we go? We go left. Okay, so if current.left is none, I've found the right place to insert this thing. Okay, so let me put it there. Cur.left gets, we're going to make a new node. We're going to insert that leaf onto the end, and the tree node takes 2 parameter. The key that you want to insert, okay, so that's given by the key parameter, and the value you want to associate with that key, that's given by the value parameter. Okay, that's that part. Now if cur.left is not none, in other words, there's something there, we make our recursive call. Else, self.insert, right? I have to call self because I'm in a class here, you calling class method. I need to insert on the left child, so cur.left, and then pass it the data, the same key and the same value. This is the recursive call. All right. So else if the key is greater than current.key, what do we want to do? Well, all right, we're trying to insert the key value 55, and the current value is 5. We got to go to the right. Okay, so if cur.right is none, great, I have found the right place to insert it. Okay, if you're getting kind of confused by all this, just go back to your map here, trying to understand what's going on. These values are your keys here. We just happen to be inserting a second value that's associated with it. But these values are your keys. Make sure, it's going to go a long way to helping you debug this thing if you have a really good concept of how insert works at this level. All right. So we're inserting to the right. Else, the right ain't blank. There's not room there. So we recursively call insert on the right child. Okay. All right. So there's a final scenario we need to handle here in our key map, our tree map, excuse me, which is when the key is already in the tree map, replace the existing tree node's value. Okay, so if the key isn't less than the current node's key and the key is not greater than the current node's key, it must be equal to key equal current.key. So replace the existing tree node's value with value. Easy. Cur dot value gets value. Okay? That's it. That's our insert code. Now while I'm here, I'm going to take care of the length function. Okay, length should return the number of nodes in the tree map, and this algorithm must have a big O of 1 implementation. So if we were silly and we wanted a big O of n implementation, we could kind of go through everything in the tree and just keep counting nodes. Or the smart thing to do would be, as we insert, we increment some counter somewhere. So in my constructor for the tree map, I'm going to initialize a size variable and initialize it to 0. And then every time I insert a key or insert a value into our tree map, I'm going to insert or increment this value. Okay, but only when I insert a node, which is when I hit my base cases. And then later, when we go to do deleting from the tree, we'll decrement this counter as well. Now len, in order to implement it, I just need to return self.size. And as long as I am updating the size when I insert stuff, this will be correct. All right, so let me run my tests and let's see what it says. Okay. Not implemented error, set item, that's okay. I haven't gotten there yet. So, set item. All right. I don't have tests for this yet because now we need to use this insert function. So I'm pretty confident this insert function is correct, or method, excuse me, is correct. But now we want to use it, right? The way that where we are going to use it is with the setItem method on our tree map. So hopefully you recall from your hash map assignment, setItem allows you to use code like this. Tree with the bracket, this is the key, gets the value. Okay, so we're going to have setItem call insert. Right? So this is pretty easy. We just need to check. What we want to do is call self.insert what? Well, where are we going to insert? We're going to insert at the root, the key, and the value. Okay. So this kicks off the recursive call to insert. Now, before we do this, though, we got to handle this one special case, and that special case is when the tree map is empty. Okay. How do you know if the tree map is empty? Well, this is the initial state of the tree map. So a tree map is empty when its root is none, or when its size is 0. Okay, so I'm going to say, all right, if self.root is none, what do you want to do? Okay, I'm saying insert the very first thing into our dictionary. All right, well, the very first thing I'm going to insert is going to be attached to the root. It is the root, the very first thing. So self.root, this is just like when you added in your linked list and it was empty. You make that first thing you add the head of the list. Here we're going to make that first thing you add the root of the tree. Self.root gets a new tree node with the key and the value that were passed in. Okay. And we also need to increment the size. Okay. Else, we're going to insert. All right. That's the code. Let's run it. Okay, I'm failing a bunch of tests because I haven't implemented them yet. But here's my setItem. Good. setItem seems to work. Constructor works. Length is working. This is a good sign because length works by testing setItem. Okay, so I'm making some progress. It's a good sign. Okay, so this is the code for insert and setItem. We're going to pause here and we're going to go back to your worksheet for the next part of this.